cube and cube root functions. I think I mentioned on Tuesday how this is going to be pretty similar to square and square root. So squares was our quadratic functions, okay, and then square root functions were their inverses, okay. The parent functions are not necessarily similar. Like the graph doesn't look the same, but the process of how we solve cubes and cube roots is the same as how we solve square and square roots. And the process of transforming the graphs is the same. Okay, you're just starting with a different parent function, but your processes of graphing and solving are similar. So first of all, what does cube mean? When we say cubic, what is that? To the third power. Okay, so our parent function for cubic is simply y equals x to the third power. That's what cube means, x cubed. Okay, what is the parent function for the cube root function? What would that look like? Say that again. So it looks like a square root. That remember that symbol is called a radical. So it's the radical symbol, but we don't say square root. Okay, to know that it's a cube root, we have to put the 3 as the index. Let me grab the phone real fast. Go write that down. Yes, yes. Yes, sir. Okay. Don, Mr. DiNardo needs you to come down with your laptop. He just said with your laptop, so just take your laptop. Okay, sorry about that. Okay, so we've got the cube parent function and the cube root. What I was explaining here is this, remember, this is called our radical symbol, and the number that shows up right here, that is called our index. So to know that this is a cube root, we have to put that 3 there. If we had the radical with no index, that's a square root. Okay, so this is the cube root of x. Now to get the graphs, if you don't remember the parent functions, we did a unit last semester. We went over all the parent functions, and so you have that as reference back from last semester if you want it. But if you don't remember it, any function ever, you can always just make yourself a table. And whether you actually write out that table or you just do it in your head, you're simply saying, if I input some number and then you calculate and you see what the output is, and then that's the point that you plot. So if you don't remember what the parent function looks like, we can just try. If I input a 0, what is 0 cubed? 0. So if I input a 0, I get an output of 0. So there's a point at 0, 0. So I'm going to start with that. Okay, what if I input a 1? What's 1 cubed? Also 1. So there's a point at 1, 1. What if I input a 2? What's 2 cubed? Remember, cubed means multiplied by itself that many 3 times. So 2 times 2 times 2. So there's a point at 2, 8. Okay, and then if I cubed 3, I would get 27. That's not going to fit on this grid. Okay, so that's as far right as I can go to plot points. But what about to the left? What if I go negative? So what if I input a -1? -1 times -1 times -1. -1. We talked about this back before spring break. Remember, if you have an odd power, your sign is going to stay the same. If your input is positive, your output will be positive. If your input is negative, your output will be negative. If it's an odd power, right? Okay, so just think about what the number cubed is and then keep the sign that's there. So a -1 cubed will still be just -1. So there's -1, -1. And then if 2 cubed is 8, what's -2 cubed? -8. So we'll have a point at -2, -8. Okay, so hopefully that kind of stirs some memories or recall, seeing those points plotted. Okay, the cubic function, it's not a straight line. There's no way to get a line through these 5 points. It is a curve. It's like that. Okay, now, this graph, when we talk about the behavior of the graph, we're talking about if it's increasing or decreasing or constant, and we determine that by reading the graph left to right. So if I were to be tracing this graph from left to right, am I increasing or decreasing? Increasing. Do I ever change? No, it's going to be increasing forever, right? So that means that there's no vertex on this graph because it doesn't change behavior or change direction. Now there is this point in the middle here that we plotted first at the origin where the shape of the graph kind of changes there, right? See how it's kind of concave to the left here? It kind of bows out left. And then after that point, that's the opposite. It bows out, is concave to the right. So it changes shape, but not behavior or direction. That point is called a point of inflection. Okay, so it says point of inflection in the parent function. That's the origin, 0, 0. Okay, so that point of inflection, it's like that center point where it kind of changes shape, but it's not technically a vertex. So far, so good? What's my domain here? All real numbers. If I look at left to right, this graph is going to go on forever. There is no input. There is no number that I could input for X that would give me a non-real number, right? I could input any negative, any positive, decimal, fraction, integer, it doesn't matter. Okay, this graph exists everywhere, left to right. There's no input that's excluded. So the domain is negative infinity to positive infinity, or you could use the all real number symbol. What about the range? Still all real numbers. It's bottom to top. Remember, range is your Y values. So it's going down forever, it's going up forever, and there's no gap or break. There's no asymptote, no hole, nothing. It is continuous from negative infinity to positive infinity for the range as well. Does that look familiar now that you see it? Okay, so that's your cubic. Okay, so cube root. If you don't recall what the cube root parent function looks like, that's okay. We can do the same strategy and say, well, if I input this, what's the output? So if I input a 0, what's the cube root of 0? 0. So also a point at 0, 0. If I input a 1, also output of 1. So a point at 1, 1. What if could I take the cube root of 2? Can you do that in your head? No, I can't. So I doubt you can. It's going to be a decimal. Okay. Think back to when we did square root functions right before spring break. That's what we tested on. I couldn't take the square root of 2 either, so I didn't bother trying to plot that. I just found my next perfect square, which was 4, and plotted that. And then found the next one, which was 9, and plotted that. So I'm not going to I'm not going to input every integer. I'm only going to plot points at the perfect cubes. Okay, I know we made a table in our notes back in Unit 8 and wrote out what the numbers cubed were. I think we went just through 5. Okay, but does anybody remember what the next perfect cube is after 1? 8. The cube root of 8 is 2. We literally just graphed the cube. We said 2 cubed was 8. So that means the cube root of 8 would give us 2, right? Works in reverse. So instead of having a point at 2, 8, this one's going to have a point at 8, 2. Very good. Now I can't go any further to the right. The next perfect cube would be 27. That's way off our grid. But I can go to the left. Okay, if can I take the negative cube root of a negative? Yeah, because it's odd. I can't take the square root of a negative because that's an even index. As long as it's an odd root, you can have a negative underneath. That's okay, it exists. And it keeps its sign. Same thing with the cube. Okay, so if you have a negative under the cube root, your output's going to be negative as well. Okay, and so we already established the cube root of 1 was 1. So the cube root of -1 is -1. So -1, -1. So those 3 points in the middle, those are the exact same 3 points from the cube. But this point over here was at 8, 2. So where do you think we should have another point? -8, -2. So there's this curve. So a very similar curve. It's just like it is kind of rotated, transformed, reflected somehow, but it's like the same shape, right? Almost. Okay, it's just going like a different direction. Now, the behavior is still the same. It is increasing left to right. If I trace it, where's the point of inflection this time? Still at 0, 0. Good. What is the domain and range this time? Still all real numbers. And I'll put on this one the all real numbers symbol. That means the same thing. So you can use this interval notation that we did here, or you can use the all real numbers symbol. Those are both correct. You need to know both. Now, we don't need to know this today. We're going to get into it more next week, but it's a good time to point it out. What you did to get these points was you switched your x and y from the cube, didn't you? Instead of 2, 8, you went 8, 2. What is that when you switch your x and y? What's that relationship called? Inverse. Very good. These are inverse functions. All of the points were switched. You just don't realize it for 1, 1 and 0, 0 because they're the same forward and backward, right? You switch 0, 0, it's still 0, 0. You switch 1, 1, it's still 1, 1. Okay, so you didn't notice it until we got to the 2, 8 versus 8, 2. But these are inverse functions. Remember, graphically, inverse functions are reflections across the line y equals x. That's why these look similar. If I were to draw them on the same graph with the line y equals x, you would see that they, if I drew that other one here, it would look like this and go here, and I folded over that line at the diagonal, everything would match up. We'll talk more about that next week. But I just wanted to point out that's what you did to get this point. You switched your x and y because these are inverse functions. Okay, so those are our parent functions that we're starting with, okay? We transform our functions from those original parent functions. Your transformation rules have not changed. These are the same transformation rules we've been using all year since you ever learned transformations back in algebra. This year we've focused on absolute value functions, quadratic functions, square root functions. It doesn't matter what the type of function you're starting with is, these transformation rules still apply. They still work the same way. Okay, the A, H, and K still show up in the same spot if we're in what's called vertex form. So here it is, the cube function in vertex form and the cube root function in vertex form. So here, we'll start with your H. So your H, notice, is inside the function. When I say inside for cube, that's inside these parentheses. It's part of what is being raised to the third power. For cube root, it's under the radical, right? It's being added or subtracted from x inside. Does anybody remember what H does to the graph? What type of transformation that is? The horizontal shift. Good. Now, this was the somewhat tricky one. It's opposite of what you think based on the sign, because the equation has a minus in it. So if you have x minus h, h itself is actually positive. Okay, so that would be shifting right when you see a minus. So when you see x minus h, it's going to shift right. When you see x plus h, that means h is technically negative and it's going to shift left. Okay, then k is added or subtracted on the outside. It's a plus in the format of vertex form. Okay, so it's straightforward, the sign that you see. Okay, and what does k represent? The vertical shift. Good. Okay, so plus k is going to shift up, minus k is going to shift down. Okay, so those are our translations. Slide, shift, up, down, left, right. Okay, now back when we did this with quadratic, if this was a square instead of a square root, this would be a quadratic function. We talked about a vertex because quadratics have a vertex, a turning point, right? And what was that vertex? If you had the equation, you could find the vertex by looking at what two values? HK, right? HK, the ordered pair, HK was the vertex of the quadratic. Or for the square root, it was that starting point or end point, whichever way you prefer to think of it. For cube and cube root, there isn't a vertex. What is there? That point of inflection. It's where it changes shape a little bit. It's not technically a vertex. It's a point of inflection. But that still happens at HK. HK still gives us a point on our graph. Okay, so HK, come on, draw, is still the first point we're going to plot when we're graphing these. Okay, now besides H and K, the other value that could transform our graph is A. Well, come on, highlight, please. Okay, A does what? It does two things. It can reflect the graph if what? If it's negative, right? If A is negative, that is a reflection across the x-axis. Very good. Now, technically, cube and cube root are kind of special cases. We have not, in any of the functions we've been dealing with, we have not talked about what if the negative was multiplied inside. That's where a b value would go. We don't need to focus on b, so we haven't been putting it in there. And normally a negative a reflects over the x-axis and a negative b reflects over the y-axis. But cube and cube root, these are actually special functions because if you reflect this over the x or the y, they look exactly the same as each other. So it doesn't matter if the reflection is over the x or over the y for these two particular functions. Okay, they're kind of special cases. Not that we're going to have any where there's a negative inside. That's just a special feature of these, something that sometimes comes up, so that you know. All right, so A being negative can reflect the graph, okay, but A in the parent functions, if we go back up here in the parent functions, is there anything in front of X being multiplied in either one of those? No, so it's an understood 1, right? So A in the parent functions is 1. So if A is something other than 1, it's going to have another effect on the graph besides a reflection. What would that be? Stretch and compression. Very good. So the stretch or compression will depend if it's not 1, is it greater than 1 or is it less than 1? Okay, so if it's greater than 1, okay, here, that's a vertical stretch. But if that A is between 0 and 1, so it's like a fraction or decimal between 0 and 1, that is a vertical compression. All right, so everybody recalls our transformation rules, right? All right, let's put it all together. The parent functions that we're starting with and our transformation rules that we just reviewed, refreshed on. I will do A with y'all here. So we've got a cube function first. The first thing I want to do is identify A, H, and K. So what is my A? Is there anything multiplied in front of the cubed piece? No, so it's an understood 1. So when A is 1, is there any stretch, compression, or reflection? No. Okay. What is H? Is there something added or subtracted inside with the X? No. See the difference in A and C example here? See how this is just X cubed, but this has parentheses, X minus 1 cubed? That's what I mean when I say inside. You would see those parentheses. It's part of what's being cubed. So here, no, there's nothing in there. So that is a 0. So there's nothing being added. Okay, and what is K? K is 5. K is what's added on the outside. So it's a positive 5 here. Okay, so we are going to describe our transformations. So A, we said had no effect. H is 0, no effect. So the only transformation here is that it's shifting up 5. The parent function shifted up 5. That's it. So the point of inflection, remember, is always HK. So here, what is that? 0, 5. Plot that. Now, once you have your point of inflection, since there is no stretch or compression, since once you plot your HK, if A is 1, you just do the same movements from your point of inflection that you did in your parent function, which was over 1, up 1, or left 1, down 1, or over 2, up 8. That's going to be off this graph, or left 2, down 8. Bless you. Now, when we start dealing with A's other than 1, that's going to change how we move from that point of inflection. Your other option is always a table, just like I told you when we were plotting the parent function. If it helps you to physically have a table of values, start with your HK and then like get some points to the left and some to the right. And say, okay, if I plug in a -1 here, what's going to happen? -1 cubed is -1 plus 5 is 4. So there should be a point at -1, 4. Yeah, that's that point I plotted by going left 1, down 1. So if you prefer to get that point by making a table, that's fine. Okay, if I plugged in a 1, 1 cubed is 1 plus 5 is 6. There should be a point at 1, 6. Yeah, that's the one I got by going over 1, up 1. So you can always get those points by making a table as well. Does that make sense? Okay. Domain and range here. All reals. Let's visualize something with these parent functions real fast before we go on to the next one. Looking at both of these. Is there any type of transformation that you think might change the domain or range from all real numbers? If I move either of these graphs up, down, left, right, reflect over either axis, or I stretch or compress in any direction, will it ever not go on forever in both directions? No. There's no transformation that's going to take place that is going to change this domain or this range. Do y'all see that? So for this unit is only cube and cube root. Your answer every time for domain and range is all real numbers, or negative infinity to positive infinity. Please don't miss a domain or range question in this unit. It's all real numbers. Make sense? Okay. Well, go ahead and fill it out for all of these. And you can use whichever method is preferred for you. You can do the interval notation like this, or you can use the all real number symbols. I don't care which one you use. We'll just practice both. But I can go ahead and fill all those in because these are all cube or cube root. So I know it's all real numbers for both domain and range. Good? All right, let's go ahead and identify A, H, and K here for this example. So what is A? Yeah, understood 1. There's nothing here in front of the radical, no coefficient, so it's an understood 1. What is H? So it's x plus 3, and remember in the vertex form of the equation, it's an x minus h. So we said when you see a minus, it's the opposite, right? So that means if we see a plus, h is actually negative 3, which means this is going left 3. Now the a had no effect. A being 1, that's the same as the parent function. Okay, what about k? Positive 2, so what's the transformation? Up 2, good. So my HK, my point of inflection, is at negative 3, 2. So I'm going to plot that. And then I can either make a table of values, or I can just count my movements from the point of inflection. I know I should, because A is 1, there's no reflection, no stretch or compression. It's going to be the same movements as the parent function. So it's going to be over 1, up 1, or left 1, down 1. Or again, from the point of inflection, it's going to be over 8, up 2. This is a cube root. Make sure you're looking at the right parent function. So over 8, up 2. If I go left 8, down 2, be off the grid a little bit. Feel okay about that? All right. Let's go ahead and do C. Still no A. A is 1 here. I'm going to go ahead while I've got my pink pen here. Go ahead and tell me A in part D. Finally, we're going to have one over there where A is something other than 1. It's a negative 2 in front. Okay, in part C, what is H? Yes, H is a positive 1, because remember, it's the opposite sign that you see there. Is there a H over here in D? No, there's nothing under the radical with the x being added or subtracted. All right, what about K? Yeah, in C, it's negative 4. Anything over here? 0. There's nothing added or subtracted inside or outside over there. All right, so here the H would move us right 1, and the K would move us down 4. Okay, our HK is at 1, negative 4. no stretch or compression, no reflection. So it's a cubic. I can just count from that point of inflection over 1 up 1, left 1 down 1, over 2 up 8. And this one would be off the grid if I went left 2 down 8. Everybody still with me? All right. Finally, we have one here we'll take a look at that has an A other than 1. Now, where is my point of inflection, though? Yeah, HK are both 0. So this is not translated. It's not shifting left or right or up or down. It's still centered there at the origin, that point of inflection. But what does that negative do to the graph? So it's going to reflect over the x-axis. And what does the 2 do? It's a vertical stretch. Remember, A is when that A is bigger than 1, the absolute value of A, I'm not worried about the negative. The number value of it is bigger than 1, it's going to be a stretch. So this is going to be vertically stretched and reflected. Vertical stretch and a vertical reflection. Okay, so some of you, go ahead. It'd be a vertical compression. No, the absolute value of it. We're not looking at the sign. The sign tells us the reflection, and then we're looking at just the number. That's a good question. I'll go back and show you. That's why we have absolute value bars around the A when we're talking about that. We're talking about just the number part of A, like not the sign, but the actual value. Okay? All right, so you can do 2 things. Some of you can do this in your head, like we've been doing, and just understand A is a vertical change. So it is affecting our vertical movement. So our up or down that we move from the point of inflection. So normally we go over to the right 1, up 1. So it's the up 1 that's going to change because of A. So instead of 1, it's going to be -2. So it'll be over 1, down 2. So I'll be here instead. Now, in opposite to the left, I normally go left 1, down 1. So that's a -1 movement usually, but I'm multiplying by -2, so it becomes +2. So left 1, up 2. Oops, I didn't mean to erase my point of inflection. Okay, so now you can see right away it's going the opposite direction. It's going to be decreasing instead of increasing because of the reflection. Okay, now normally we go over 8, up 2. But again, the vertical movement, the up 2 is a +2. We're multiplying by A. A is -2. What's 2 times -2? So I should be going down 4. So I'm going to go over 8, down 4. And in the opposite direction, I'm going to go left 8, up 4. So you can see that this ends up decreasing left to right instead of increasing left to right, like the parent function or the one before it. You can see normally it increases left to right. This one is reflected, so it's decreasing. Okay, and see how this one looks a little bit taller than the parent function did? It's because it's been vertically stretched. Remember, when we vertically stretch it, it's like we're putting our hands on top and bottom and pulling them apart, so it's going to look taller. Now, if that didn't make sense to you, me counting from like saying why I'm going down 2 or why I'm going down 4 instead, if you didn't follow that, that's okay. You don't have to. You can always make a table. So we know the point of inflection was 0, 0. Okay, so I need to get some points to the left and right of that. So if I pick a point to the left, so -1 for my input, I'm going to come up here and just calculate. The cube root of -1 is -1. And then what's -1 times -2? 2. So there should be a point at -1, 2. Hey, that's where I plotted a point. Okay, a point to the right. If I plug in a 1, the cube root of 1 is 1. 1 times -2 is -2. So there should be a point at 1, -2. Okay, and then you could say, okay, normally I go over 8 and then that's a 2, but let's try it. If I take the cube root of 8, that's 2. -2 times 2 is -4. That's why I have a point at 8, -4. Now, I know we're taking notes right now and learning how to do this by hand, but what's another option? If you had your laptop open, what could you also do? You could go to Desmos and plug this in and look at the graph, or make a table in Desmos if you prefer to do it that way. You'll feel okay about that? Okay. So let's flip over to the back. Let's identify our A. What is A here? 3. And so what is that going to do to my graph? What type of transformation is A? That's a vertical stretch because 3 is greater than 1. Okay, so a vertical stretch. Okay, what is H? It's going to be, yeah, it's the opposite sign, remember, so it's going to be -1. So what does that do to my graph? Good. Left 1. And my K? Yeah, there is no K. It's a 0, so there's no up or down shift. So what is my point of inflection? -1, 0. It's HK. So -1, 0. That's where I plot first. And I'm going to start from there. Now this time there is a vertical stretch again. So instead of over 1, up 1, I should go over 1. Now it's not negative, so I'm not switching direction. Okay, so it's still going to be the same direction. But instead of up 1, how much should I go up? 3. Yeah, multiplying by 3. So over 1, up 3. You can make a table if that's easier for you. Normally I go over 2, up 8. What's 8 times 3? That's going to be off this grid. I can't plot that point. It's too high. What about to the left? I normally go left 1, down 1, but this time I'm going to go left 1, down 3. And again, I wouldn't be able to fit the other point because it'd be down 24 from there. So I can only fit those 3. And I know right away my domain and range, I could have done this first, is all real numbers. I don't even have to see the graph. I just need to see that it's cube or cube root, and I know it's all real numbers. Go ahead and write all real numbers here. All right, what's A? 1/2. Okay, phone again, hang on. Yes, sir. Case This goes real fast.
Don't understand.
I don't think so. All right, so what is 1/2 do to our graph for if that's our A value? Good. When A was greater than 1, it was a vertical stretch. 1/2 is less than 1, so it's a vertical compression. All right, H. Good, and that is going to be left 1, same as the last one. And K. And that will do down 5. Good. So what's HK? So I'll start at -1, -5. Go ahead, go. There's no new assignment today. Just finish that Delta math from Tuesday if you haven't. All right. Now this time I do have an A. I'm going to zoom in on this graph so y'all can see me counting a little better. Okay, normally we're a cube root, so normally it's over 1 up 1, but I'm going to go over 1 up half. So I'm not going to be on one of the intersections of the grid lines, right? Same thing to the left. Left 1 down half. Okay, and then normally it's over 8 up 2. But half of 2 is 1, so I'm going to go up 1. So over 8. There we go. How do you feel about graphing? Good. I think it's pretty straightforward, and especially when y'all get to use Desmos, it should make it even easier. But you just need to understand there's going to be questions that Desmos won't answer, like if identifying your transformations. Desmos isn't going to tell you that. It's just going to show you a picture of the graph. You have to be able to describe that. Okay, that's what we're going to do here. This part won't take long at all. We're describing transformations. So I'm going to just say, what is A? Since I'm going to color code this, I'm going to do all the A's first. What's A in this first one? Good. A here. Good. Now, when A was 1, that's no transformations, right? But when A is 4, that's a vertical stretch. Okay. What's A here? -1. So that's a reflection over the x-axis. Okay, and what's A here? So that's a what? Vertical compression. So that's all the possible A changes. No change, reflection, vertical stretch, or vertical compression. What about H? What's H in the first one here? +7, so that is right 7. H here is 0. It's not under the radical. It's not an H. Okay, here H is -3 because it's the opposite. So that's left 3. And here H is +2. So that's right 2. Good. So then the last but not least is K. I'm going to finish this up. So if the bell rings, y'all can watch this video to get the rest of this. Okay, so K here is 2, which is up 2. K here is -1, which is down 1. K here is nothing. There's nothing added or subtracted outside, so no change there. And K here is -6, so it's down 6. Y'all be sure, I'm going to finish up this last example. The exit ticket is for y'all to try before you come back to class. So make sure you try at least that exit ticket. This one is simply the reverse of what we just did. Instead of being given the equation and describing the transformation, we're given a description and we want to write the equation. So it's actually pretty simple because they tell us we are shifting 7 units left. That tells me H. H is -7. We are shifting, it says 1 unit down, so that tells me K is -1. And then it tells me we're reflected across the x-axis. So that tells me A is negative. They don't say anything about a stretch or a compression, so it's a 1. So then you just write your equation with that A, H, and K. So it would be negative, and it's a cubic. So x plus 7 cubed, because remember you do the opposite of H, and then you're minus 1. And that's that. Then on B, instead of telling us the description of the shifts, they just tell us the turning point or the point of inflection. That is your H and your K. Remember, that is HK. They don't say anything about a stretch or reflection or compression, so A is assumed to be 1. This one is a cube root. So it would be A is an understood 1, and then it would be the cube root of x, and then H is inside as the opposite, so plus 2, and then K is outside, so plus 3 on the outside. So those would be your equations. So you need to be able to go from equation to description, from description to equation. And then you need to try exit ticket, and we'll go over that tomorrow. Okay, sorry, I was finishing a recording. What's up?
What are we doing tomorrow?
We're going to be practicing what we're learning today.
Okay.
And doing a FA.
Because I'm going to be going for UAL tomorrow.
Okay, so I'll have it. It'll be on the calendar on Canvas where the assignment. I think it's an Alex. I made it the other day, but I'm trying to remember if I did it in Delta Math or Alex. I think I did it in Alex, but I'll put that on the calendar, and then we'll be doing a FA, which is in Aware.